I don't have any huge announcements today other than a reminder that your homework is out there. It's been a week since it was out there, and I would strongly recommend that if you haven't started already, start it soon. Um, it could take some time. Uh, so that's really the only real announcement. Any questions about uh, this homework if you started? There are no questions. I do have a comment. This came up in office hours the other day. There's an extra credit question in this homework, and it can either take a lot of time or you can just read the answer of a 1987 paper from a journal called Machine Learning. The name of the paper is Learning Decision Lists. I'm not sure which one's easier, solving it yourself or actually reading the paper. I'll leave it to you. Either one's okay. If you read the paper and base your answer on that, make sure that you cite it and let us know that you read the paper. The paper actually is more general than what this question asks. There's a question on the lecture from Tuesday, uploading the lecture. I'm behind on that. I'm really hoping to get all the lectures up to date on YouTube by tonight. Other questions? Yes.
Actually, could we do the remapping for the linear to be more specific, original the value of the conditions like 0 or 1 could map to -1 and 1.
Yeah, sure.
Okay.
Yeah.
Thank you.
Okay. If there are no big points to discuss, I want to continue where we left off. Turns out we are about a week behind the plan that I had, so I need to somehow catch up. We were talking about ensembles and more specifically about boosting. I'm going to quickly go do there's a big question. What's a good way to check? This is a good question. So I'm going to just answer this. How do you know that your proof is right? If the proof is a heavy proof, how do you know that your proof is right? If you're doing some heavy lifting, and that's a non-trivial question, it turns out. The correctness of a proof really depends on the correctness of the arguments and the way in which these arguments are structured. There's no magic answer here, unfortunately. If you feel like you want to discuss your proof, come talk to us. We'll kind of give you some pointers on whether you're on the right path or not. There's no general answer that says that checks your proof. It turns out it's a mathematically difficult question to know whether the proof is right or not in a technical sense. So come talk to us, and we'll kind of help you. If there are any course corrections necessary, we'll help you around. And if there are also, feel free to discuss on Canvas without actually giving away the answer. Think about, I tried this idea or something like that.
Canvas or Piazza?
Piazza, sorry, I always say Canvas. My default in my head for discussion is still Canvas, but Piazza, yeah. But, make sure you don't give away the answer with that caveat. Okay, boosting. So the origin story here is a question that came from a 1988 paper that asked, if I know that a certain concept class is weakly learnable, does this mean it's strongly learnable? And by weak learnability, what that paper meant was, if it's easy to construct rules of thumb, even a data set, that are slightly better than chance. Each rule of thumb is slightly better than chance at getting the right answer. Does this mean that there exists some algorithm that can produce a model that is arbitrarily close to perfect, or that has as low error as possible? And this was a theoretical question. And the answer to this came in the form of an algorithm in 1989, which then kind of was updated, eventually led to a 1995 paper that introduced an algorithm called Adams, and that's what we're looking at. Adams operates by assigning a weight, or I'm calling it a distribution here, assigning a weight for each training example. And then the algorithm itself proceeds in many rounds. In each round, there's a current set of weights assigned to each example. And the weight here refers to the importance for each example. The weight of an example is the importance for that example in this particular round. So we have d sub t of I. So I goes from 1 to n. First, you construct this distribution dt, and then you call whatever learning algorithm you want that provides that constructs a weak hypothesis. The only difference from the regular sort of learning algorithms that you've encountered so far is this algorithm needs to respect these weights. So it needs to somehow know that an example that is assigned more importance should be actually treated as more important. And you can think about how to modify your algorithm, the existing algorithms that way. For example, there was we had a discussion about this in class the other day. One way to modify your perceptron algorithm to respect these weights is to change the learning rate for each example. For an example that's more important, you take a bigger step size. For an example that's less important, you take a smaller step size. Anyway, so you call the weak learner on this weighted data, and you get a weak hypothesis. And then learning keeps this goes back here, and you update the distribution because now you're in a new round. You call the weak learner again, you get a weak hypothesis. Each of them, let's call that H sub t. And each HT is a classifier. It takes an input and produces a label. And the guarantee that you get is that classifier is slightly better than chance. We have capital T such classifiers. Somehow you need to combine all of them together to construct a consensus model, or to be more correct, or to be more, to use the word that is more commonly used, to construct an ensemble, a prediction rule that calls each of these experts, weak experts, to get a label and combine them. This is like a high-level summary of the boosting algorithm. The middle step here, namely this step, is easy. In the sense, you can use whatever learning algorithm you want in that case. So the only things that are left to be described are how do you construct a distribution on each example, and how do you construct this ensemble? How do you construct the final output by combining all these weak hypotheses? Any questions about where we are right now? Yeah.
So just take a perceptual example. We said we can choosing different learning rate to be different weak hypotheses.
Yes. No. For each example. So you have a distribution d sub t for each example. The way this might look is, I'll just give you a small. So let's say you have 4 examples in your data. So x1, y1, x2, y2. Right? This is your standard kind of a data set. There are 4 of them. I'm going to assign D1, D2, and so maybe D1 is 0.5, D2 is 0.25. This means example 1 gets most of the importance in this particular round. So the algorithm has to try to get, when x1 is presented, it should try to make sure that the label is y1. And example 3 and 4 have the lowest importance. By the way, notice that these add up to 1, which is just a requirement for AdaBoost. And the one way of doing this is I can have a learning rate, right? So, if the example makes a mistake on x1 or xi, then I update my weights is w plus r yi xi. Yeah, if it makes a mistake. Now, the question is, how do we make sure that a mistake on x1 is more important than a mistake on x4? That's what the weighted, the cost sensitive, it's called the cost sensitive learner. That's what the cost sensitive learner has to do. And the way it might do that is to say this learning rate, R, is some constant, some learning rate that you find using your hyperparameter tuning times d of I. And this is no longer, it really becomes Ri. The learning rate is, so for the first example, the step size is bigger than the step size for the last example. And this makes sure that your perceptron is cost sensitive. And it turns out this applies for any algorithm that uses stochastic gradient descent. You just change the learning rate, it becomes cost sensitive. Okay, but this is what I've just answered is yes.
You said that the weights have to add up to one.
Yeah.
But why do they have to add up to one?
In general, for cost sensitive learning, they don't need to. It turns out for Adabus, for the theory to work out, the weights add up to one. That's why they call it a distribution. It's treated as, so the intuition here is you are constructing a distribution over the training data such that some examples have a higher probability of showing up. So rather than resampling so that x1 shows up half the time, you just assign, you redistribute you basically you take the data set and you assign it. You construct a distribution such that some examples are more quote unquote problem. So it's treated as a distribution. And that's why in the way the algorithm is described, I don't call it a weight, I call it a distribution. Yes. In this case, it does not, right? There is a sequence here. In this case, it's for Adaboost, you are training them. Wait, are you talking about training or prediction? Are you talking about training or prediction? Okay. So in Adaboost, the classifiers are constructed one at a time, because you see there's a dependency. First, you construct a distribution, you find a weak hypothesis, and the goal is to minimize the weighted error. Weighted error being the error assigned, the total probability mass according to this distribution assigned to the mistakes. So next time I want to change the distribution based on the error. So if there's a dependency between each classifier that's constructed in Adaboost. Other ensembling algorithms don't have that. What do you mean? I'm not talking about computational efficiency here. Ensembling can be computationally expensive because you're not learning. Even here, right? I mean, you have to train T different models. It can be computationally expensive, and that's one of the reasons why we don't always see ensembles because it takes this much time to train one model, and you want to train T of them. You're just blowing up you're increasing the complexity. So yeah. Other questions? So what we're going to do now is specify those two things that are missing to complete the algorithm. So first, I'll talk about how to construct the distribution, and I'm going to present it to you as if this is the ground truth. The reason I'm doing that is because what I'm actually building up to is an algorithm called Adaboost. And it turns out these choices that I'm going to present are directly responsible for the theory that supports this argument. I'll only present the theorem, I won't prove it. And these choices make the theorem work. So the first point is, how do we assign the distribution for each example? So this distribution changes at each round. So D sub T is a set of weights in the Tth round. And the goal is that every round, the weak learner tries to find a classifier that emphasizes examples that have a higher D. In the beginning, we need to somehow initialize this process. In the beginning, all examples are equally important. So if you have m examples, d1 of t, d1 of I for every I is 1 over m. So it's a uniform distribution. This seems reasonable. And in fact, implicitly, this is what we've always been assuming with all the learning algorithms we've encountered so far, that all examples are equally important. Then, let's say that we've run this process for t rounds. What we have at hand right now, after the tth round is done, is we have the distribution dt that was used in this round. We have the hypothesis ht that was learned in this round. And we also know the error of the hypothesis on the training data. And by error, this is the weighted error in this round. And just to remind you, this is simply the sum over I, where I is in examples where ht of xi not equal to yi. So take all the examples where the current hypothesis made a mistake, add up their weights, and that's your weighted error. So we have access to all these three things. And the recipe now says, gives you, that I'm going to describe, will show you how to construct the t plus 1 using these three things. Before the formal notation, I want to talk about what we want from dt plus 1. So what we would like is, in the current hypothesis, in the current round, some examples were correctly predicted and some examples were incorrectly predicted. In the next round, we want our weak learner to focus on those examples where the current hypothesis made a mistake. And we don't really care about those examples where the current hypothesis was not right. So essentially what we want is to increase the importance, increase the weight assigned to examples where the current hypothesis makes a mistake. And for those examples where the current hypothesis is correct, we want to make it less important in the next round. This is the intuition that that this recipe will actually instantiate. Any questions about this, the intuition?
How do we make sure that in downloading the hypothesis, this gave the right result in the previous class? Now does not give a wrong result. Like, how do we not expect
We could. In fact, it's entirely possible that there's an example that gets upvoted in round 1 at the end of round 1 because there was a mistake. In round 2, the hypothesis corrects it, it gets downvoted. Then because it got downvoted, the next one makes a mistake. So this keeps going up and down again. Again, we don't care. The theory still works out. Why does it work out? Because there's a theorem attached to it. I'm not going to prove the theorem, but the theorem is a very, very strong result. I'll tell you how the upvoting and downvoting actually is instantiated. So let's say that we are considering one example, the ith example. I'm going to define the dt plus 1 of I in the following way. It is the previous weight associated with it. Ignore the zt for now because this doesn't depend on I. The previous weight associated with it, multiply with an e power minus alpha if the current classifier was correct, if yi equals h of xi. And if it is not correct, in this case, there's a mistake, Then you multiply it with e power plus alpha. So what, this is just the mechanics of it. But let's kind of think about what's going on. For now, assume that alpha t is a positive number. It will be a positive number. We'll see why. For now, let's pretend that we know that alpha t is always positive. If alpha t is positive, e power minus alpha t is going to be a number between 0 and 1. Right? Which means I'm multiplying the old t with a number between 0 and 1, which means I'm making it less important. I'm reducing the value. And when does that happen? When yi equals h of xi. If the example was correctly predicted, I'm multiplying its weight by a number between 0 and 1. If the example was incorrectly predicted, we'll be multiplying with e power alpha t. Alpha t is a positive number. E power alpha t is going to be more than 1. So we're going to make it more important. So on examples that are incorrect, in the next round, that example becomes more important. On examples that were correct, let's not waste the learner's effort trying to get that example right again, because we have a classifier that knows how to predict on that example. Now, I can combine these two things, because notice that now this part is must either be what comes next is going to be either very familiar or kind of weird. Notice that I have a minus here and a plus here. So e power something multiplied by alpha t. This thing here is either a minus if yi equals h of xi, and plus if yi not equal to h of xi. Both yi and h of xi are binary, -1 or 1. So when yi equals h of xi, the product of them is positive. Right? Both of them are positive. If yi is +1, h of xi is +1, the product is positive. If both of them are negative, the product is still positive. This means I can remove that and say if yi h of xi is +1. And in the other case, it's a plus if yi h of xi have opposite signs, which means it's equal to -1. Notice that when this is a plus, I need to put a minus. When this is a minus, I need to put a plus. So I can combine them both and say I'm multiplying dt of I with e power minus alpha times yi h of xi. Yes.
Yeah, so you told earlier that the sum of d will be 1.
Yes.
1, and we are increasing and increasing it.
Yes.
Such that it will stay 1. Right?
Not yet. That's the job of the z. The job of z is to make sure that all the d's add up to 1. It's a normalizing constant. And it depends, and you can imagine how, can someone tell me what the value of zt would be, given that this is the case? It's the sum of what? Well, not the di, right? Di times e power. So we have this zt is simply sum over I dt of I times now if dt was this, then all the dt plus 1 will add up to 1. Ask me questions. Yes.
So for the T round, if we want to find the best hypothesis function, we need to traverse all the hypothesis space.
That's the learner's job. The weak learner has to do something. In fact, in this particular case, for AdaBoost, the requirement of the weak learner is actually rather weak. It does not need to find the best hypothesis. All it needs is to find a classifier that's slightly better than chance. That's all we care about. So it could do something not particularly smart. Yes.
So when the model was calculated how
Yes.
so I guess why are we shrinking the eye or
Why are we reducing the, because on that particular example, we already have a classifier that, so, okay, let's kind of go back to the, oh, there's also a question on, I'll come to the question on Zoom in a minute. The abstract idea here is we are building a committee of classifiers, each of the H1, H2, and so on. And each HI is like a local expert on some kinds of examples. And let's say that we have already, H1 is an expert on examples that occur in this region. We really don't care about that region anymore, so we're going to shrink that because we already have an expert there, and let the learner focus on other kinds of examples. And it's the job of that final combining thing to make sure that all these voices are appropriately weighted. So the question on Zoom is, what's the term in the exponent of Z? I'm missing something. There's no exponent on Z. This is ZT. So let me read it out. ZT is simply the sum of what I'm drawing a box around. ZT is the sum of just that. E power, oh, it's this expression and this expression are identical. I think that's what you're asking. And this is also one of the reasons why I'm not fond of people submitting handwritten solutions, because look at how I write. So Z is a normalization constant that ensures that the dt plus 1 still adds up to 1. And even if, while I wrote the answer of for what the value of ZT would be, I want you to try to reconstruct it on your own. It should not be terribly hard. Now, the only thing left here is, what is this alpha? I just brought in an alpha and I said, I'm going to produce an alpha that is always guaranteed to be positive. Add a boost also specifies what the value of alpha should be. It says alpha is simply half log of 1 minus epsilon t divided by epsilon t. Let's unpack this quantity a bit. So alpha t is epsilon t is the weighted error at the tth round of the tth hypothesis. So we know that the weak learner always produces a classifier that is better than chance. That means epsilon t is going to be less than half. If epsilon t is less than half, 1 minus epsilon t is going to be more than half. So this quantity here is more than half, and this quantity here is less than half. So the numerator is bigger than the denominator. So this whole thing that I'm going to, this whole thing here is greater than equal to 1. The number more than, well, is that what it is? Yeah, it's a number more than 1. If it's a number more than 1, log of that is a positive quantity. So that's why alpha t is guaranteed to be a positive quantity. This also gives you a recipe for when to stop. If you keep training your weak classifiers, at some point you find that you have an epsilon t that is more than half, meaning it is worse than chance. That means you basically scrape the bottom of the barrel, because this is a classifier. What does it mean if epsilon t is more than half? It means you have a classifier whose error is a binary task with equal pluses and minuses. You have a classifier whose error is better than random. Sorry, worse than random guessing. Which means what you should do is you take that classifier. If the classifier says plus, you return minus. If the classifier says minus, you return plus. You just change the label that the classifier provides, and you do better than chance. Right? So if your epsilon t is more than half, stop the iterations because alpha t is going to be negative. Any questions about this, what we've seen so far? Eventually, it turns out the same alpha t will also be a vote assigned to each hypothesis in the final classifier. Yes. No, if epsilon t is more than half, then you have a worse than chance classifier, which means it might as well not exist, right? If you have a decision rule that is guaranteed to be 100% wrong, that means you also have a decision rule that's guaranteed to be 100% right for a binary system, for a binary classification problem. Because all you have to do is call that decision rule, and whatever it says, you reverse the answer, you get 100% accuracy. Right? If your epsilon t is more than half, whatever it says, you reverse the answer, you get something that's better than whose error is less than half. But instead of doing that, what's the point? Just stop the learning, because it breaks the assumption that Adapoost is built on, that your weak learner is better than chance. So there's no reason to go on. Most likely, what will happen is we will hardly ever get to that point in practice. That will require far too many iterations. Did you have a question?
Yeah, I guess for the same thing.
Oh, epsilon, it's an error. It's a weight. It's the sum of the dt's. So epsilon t, remember, is the sum of dt of I, where I is, I'm not writing that again, where I is all the examples where there was an error. The dt is a positive, remains positive always, because dt of d1 of I is 1 over m, and you're always multiplying by a positive number. So the d always, it's a distribution. It's always a number between 0 and 1. So you're adding them up, it's going to be a positive number. Other questions? So what we've done right now is, what I've shown you is how to construct dt at the end of each round, using the information that's available at the end of that round. Just to recap, the information that's available at the end of a round is the previous distribution. If you're at the end of the tth round, we have dt. We have the hypothesis that was just recently learned in this round, and we also know the value of the error. So using the error, we can compute alpha t, and using the alpha t, you can upweight or downweight each example based on whether it was a mistake or not. And then you just normalize the whole thing, and you get dt plus 1. I see 2 heads nodding. I think that means that everyone got it right. Okay, I see 2 more heads nodding. I don't know if you're just nodding or got it. But I'm going to charge. Yes. Each inside the week.
And then so like
No. So that takes me back here. All these epochs and everything happens inside this. And so you. Oh, I see. I would, technically you're right, but I would like to kind of compartmentalize it. The weak learner does whatever it does. Internally, it could be training for 20 epochs. Internally, it's just, randomly throwing darts. Let's not, this doesn't depend on that. As long as the weak learner guarantees that the output has a small weighted error, we don't really care. So what we have seen just now is the answer to the first question. How do you construct a distribution? I just showed you how to do it. The only thing that's left is how do you construct the final output? The final output is constructed at the end of capital T rounds. At the end of that, we have T weak classifiers, H1, H2 till Ht. And each of them also has an associated value alpha T, which is computed on alpha T while we were right after we trained that, right after we finished training the classifier, because we needed to use that for upvoting and downvoting examples. Each weak classifier is also a classifier. It takes an example and produces a -1 or a +1. And the way we combine all of them to produce a final hypothesis is you call each of those weak classifiers Ht of x on the example to get a -1 or a +1. And then we remember also that each alpha is a positive number. And then for the output of the T classifier gets a vote equal to alpha T. So you add up all the votes. So alpha T times Ht, you add them over T equals 1 to capital T, you get a number. If that number is positive, the final classifier returns a +1. If that number is negative, it returns a -1. So what we have here is basically a linear classifier that operates on top of the outputs of these weak classifiers. Any questions? Every time you encounter this sort of a description of the mechanics of an algorithm, it's worth thinking about what you would do to implement it. Because what are all the choices that you need to make in order to implement it, and how hard or easy experiments with this might be. For example, you could think of using this for your project. Not saying you should, but you could. Let's put all of this together. This gives us the full AdaBoost algorithm. We are operating in the supervised setting. We are operating in the binary classification setting. So we assume that we have a training set consisting of m examples, and each example has a label which could either be -1 or 1. The beginning, we start off by initializing the D1. Each example is equally important, so D1 of I is nothing but 1 over m if we have m examples. Then we start this whole AdaBoost process. This sequence of iterations goes on for T steps, and T is one more hyperparameter because we didn't have enough. So in each round, what we do is we call the weak learner, and we get a classifier Ht whose weighted classification error is better than chance, meaning less than half. Then you compute the vote that this classifier is going to get in the final classifier. That's nothing but alpha T. Alpha T is half log 1 minus epsilon divided by epsilon. Epsilon is the weighted classification error. Then you use the vote to also update the weights, the training examples, using the scheme that I just showed. And we are done with this round. We've trained the classifiers. We are ready for the T plus 1th round because we already have dt plus 1. We do this for capital T steps. And finally, we return the final hypothesis, which is a function. It predicts labels by taking the weighted average of the prediction of the weak classifiers. And the weights assigned to each weak classifier is nothing but alpha T. This is the entirety of the AdaBoost algorithm. It is deceptively simple. I say deceptively simple because this step can be expensive because you're calling a learning algorithm inside that, right? And also the other thing that is kind of the other complexity that's hidden here is the final output of this is not one classifier, but capital T classifiers and their alphas. And at prediction time, you need to call all of them and get their outputs and then aggregate them this way. So it's a little bit of extra work. Well, it could be quite a bit of extra work. Just to kind of give this and put this in context, some of you mentioned to me that training a decision tree was slow, right? For your homework or for your project. Imagine not training one tree, but capital T trees. Let's say T equals 100. Can take quite a while. And this is not, you can't parallelize because the choice of the classifier at the Tth round directly influences alpha, which influences dt, which influences the next classifier. So this has to proceed in a sequence. So this can be a bit, it takes some effort. Yes.
Are there like many algorithms that parallelize the algorithm, like algorithms?
There is a whole line of work on parallelizing training, and there are some very cool results. One of my favorite ones, which I'm not going to talk about at all because we've not yet talked about stochastic gradient descent in sufficient detail. There's something called hog-wild, which just says, yeah, if you have these sorts of sequential dependencies, pretend they don't exist. Things will work out. And that's not just an informal statement. It turns out it counts with the theorem. But in this case, I don't think there is one like that. Yes. That's an excellent question. Nothing here says you should. You could use anything inside each round. That's a very good observation. One interesting thing here, yes. Hogwild, Hogwild. Okay, now the interesting thing here with AdaBoost is your final classifier, going back to the example that we saw in the last lecture, might look something like this. There are three rules, H1, H2, and H3, and the final output is alpha 1 times the prediction of H1 plus alpha 2 times the prediction of H2 plus alpha 3 times the prediction of H3. Remember from the if you remember from the previous class, each of these H's can either be a vertical line or a horizontal line. But when we combine these three like this together, we end up with a hypothesis whose decision boundary is none of the weak classifiers. We are getting a more complex decision boundary by taking the weighted average. And that's why the boosted hypothesis can do better than any of the weak classifiers. You are basically making it more complex. You are allowing the final classifier to be able to partition the instance space in ways that any of the weak classifiers cannot even reach. So you're allowing more expressiveness. I just presented an algorithm. Don't trust people who just present algorithms without a proof that it works. It could be anything, right? So I'll also show you a formal result. There's actually quite a bit of formalization of this that came after this, but I'm going to show you just one. The AdaBoost theorem kind of it presents a neat claim. Suppose you run AdaBoost for 3 rounds, and at each step, the error of the weak classifier is epsilon b. We know that the error of the weak classifier is better than chance, meaning its error is less than half by definition. So let's say it's half minus gamma t. Now let's say gamma is the highest of all of those things. Okay. Just a notation. Now, the training error of the final classifier, and only the final classifier, is going to be less than e power minus 2 gamma square capital T. So let's just, the second point here simply says we have a weak learner. We have a learner whose error is going to be better than chance. We don't care anything, we don't need anything more than that. It's better than chance. It's less than half. The interesting point here is look at the dependency on the number of rounds on the training error. The training error is less than e power minus capital T. That's a 2 gamma square there, which means as T increases, the training error drops exponentially. which is pretty neat. What that means is you will end up getting a consistent, eventually it will go down to zero, because the training error is simply the fraction of training examples that um, that that are misclassified. Eventually it will go down to zero, which means you will get a consistent model, a model that's consistent with the training set. At that point, you can apply all the pack bounds that we had on the consistent learners, and we're done. Have we done? There must be a catch here. Can someone see a catch? Yes.
Really fascinating.
Sure. That's just a, let's pretend that I give you $1 million of Amazon cloud credit. You can run whatever you want. That's right. You might end up overfitting because you see this picture must hopefully give a hint. We are going to keep drawing lines till every training example is correctly classified. So we might end up overfitting the training set. AdaBoost can overfit. Keep that thought in mind, and we'll come back to sort of a peculiar observation after that in a bit. This theorem is not terribly hard to prove. There's a pointer to the proof on the class website. It's a bit involved, and that's the reason why I'm not going into it in the class. But if you're interested, check out the proof. It's a fun proof. And as you go through the proof, you'll realize that all these choices of how D gets updated, how alpha is computed, how the final classifier is weighted in a certain way, all of those things are defined so that the proof works. So the question to think about is it sufficient to upper bound the training error? And the answer is, if we can do that, then we can start using those results that we've seen from PAC on generalization error. But generalization error is going to be no more than training error plus something. And so it's going to be bounded. It's also going to be bounded. The cool thing is, in practice, the AdaBoost training error does actually drop down exponentially very quickly. As long as the weak classifiers are all better than chance. I don't remember which data set this is, but it drops down very rapidly to zero. That doesn't mean that each weak classifier is getting better. In fact, as T increases, the weak classifiers are training on more and more difficult examples, or are emphasizing more and more difficult or noisy examples. That means as T increases, the error of each classifier actually tends to increase. The classifiers get less and less important, but the training error goes down. But we don't care about the training error. Our goal is generalization. Everything we know about the overfitting and such things should tell us that the training error might reduce to zero, but because the model is overfitting, the test error should eventually keep increasing because you're overfitting the noise. The final hypothesis, another way of thinking about it is the final hypothesis, H final, will end up partitioning all the examples so that every example is correctly predicted, which means the hypothesis itself becomes too complex. And our Occam's razor theorem tells us that its generalization error can get arbitrarily worse because it's overfitting. Except in practice, AdaBoost does something quite interesting. Across many different data sets, the training error does indeed go down to zero, and the generalization error seems to plateau. So it doesn't get worse as the model gets bigger. And these observations led to a flurry of papers trying to explain what's going on here. There are a few different versions of these explanations. Oh yeah, there's another sort of a very odd thing that has been observed. Even after the training error hit zero, generalization error actually goes down a bit. I know, it's just strange. And there's a paper from 97 that tries to explain it, and I'm not sure I fully buy the explanation, but it's also, I'm not sure I fully disagree with the explanation. I'll leave it to you to decide if you're interested. Very briefly, the Adaboost is a rather simple algorithm for constructing an ensemble. All you need to decide is how many elements you need in that ensemble. That's your capital T. You can use it with any weak learning algorithm, which means you only need classifiers that are better than chance. And the caveat is that it can overfit. It can you have to, there's a computational question. The performance depends on which data set you use and what your weak learners are, of course. I mean, these choices, you don't get something for free. If your weak learners are too complex, then your the final Adaboost hypothesis might be even more complex and it will tend to overfit the noise in the data. If your weak learners are too weak, then you might have to run for many, many, many rounds to see something meaningful. There's a question.
So by 2 weeks, they mean still better than 50%.
Still better than 50%, but not too great. Yeah. Then you have to collect too many of them to see something meaningful. There's this really nice work from by Rich Caruana and his student from 2006 that showed that at that time, if you take the decision tree learner that you have, right, the ID3 algorithm, but rather than constructing a full decision tree, you construct a decision stump. A decision stump is a tree of depth 1, and make that your weak learner. And then you apply Adaboost and you basically build a boosted decision stumps. What they showed was if you have a small number of features, typically kind of descriptive features of some sort, a few hundreds of them, for such tasks, it's a very hard learning system to beat. Boosted decision stumps tend to be a very good classifier for many, many different kinds of data. And this was a massive empirical study for that time. Today, by today's standards, this is like a normal size paper, but by 2006 standards, this was just incredibly complex. They ran, I think, maybe about 8 or 9 different types of learning algorithms on about 20 or 30 types of data sets. And the consistent winner was boosted decision stumps. This insight, this advice might change to might be different today because neural networks, we understand how to train neural networks better.
So for that, do you just remove the feature that is like those decisions that fits? Remove that and then decide the next.
No, you don't remove anything. You don't. So because in a different round, there's a weight associated, right? Sort of a good exercise question is to think about how to modify the ID3 algorithm so that the weights are respected. And the hint here is you change how the entropies are calculated. But the weight takes care. It's possible that the same feature gets picked again. Questions? Other questions? Adaboost is not terribly hard to implement. The only thing you need to change is how your weak learner respects those weights. And it's worth thinking about how to implement it, and maybe you can even use it for your project. Let's generalize this from this specific instance of an ensemble to something more, something less concrete. We're going to talk about ensembles in general, where I talk about boosting, bagging, and random forests. In general, ensembles are an idea that says, if I need to produce a model, if I need to produce a decision rule, rather than training one decision rule, I'm going to train many of them, a committee or an ensemble of them, and ask all of them for the answer, and then construct a consensus that tends to do better than any of these individual rules. These tend to be empirically quite robust. They also tend to be statistically quite robust because they even out any sort of oddities that might happen for any one learn. I think I mentioned this in the last lecture. the 2009 Netflix Prize winner, was a giant ensemble. We've already seen boosting. Boosting is an ensemble that is an ensembling strategy that comes with certain strong theoretical results. It says you weigh all the examples, you assign a weight for each example. In the beginning, all these weights are equal, and then you train a model on the weighted data set. Then you compute the weighted error, reweight the example so that in the next round, the examples that were misclassified become more important. And then you keep running this. And you may have to do this like maybe hundreds of times. Then you finally get away many hundreds of different classifiers, and the final decision, the way to combine the final the prediction of all these things, of all these 100 classifiers, is to assign a weight or a vote to each one of them, and you take the sign of the weighted score. We just saw this, so I'm not going to go into any detail. We want to kind of mention that boosting saw a flurry of interest in the mid to late 90s, and there were a whole bunch of papers written about boosting. So we've not talked about margins at all beyond what we saw in perceptron, but there was a few papers that argued that boosting is an algorithm that tries to maximize a certain definition of the margin. There was some work that tried to connect boosting to logistic regression, which also we will see in a bit. One interesting observation is that boosting is a linear classifier. It's a linear classifier whose inputs are not the features, but these weak classifiers themselves. So you can think of each of these weak classifiers as some sort of a learned feature transformation. You first apply all those weak classifiers, and then you just take the weighted average. I won't spend more time on boosting because we spent quite a bit of time on that. Instead, we're going to talk about a different ensembling strategy called bagging. Bagging is really simple. It's short for bootstrap aggregation. It was first described by Leo Breiman, who's a statistician. Imagine that you have a learning algorithm that can take a data set and produce a classifier. So what you do is, imagine you have m training examples. You decide that doesn't have to be m. Let's make this m. So you decide that you need n different. You want to construct an ensemble with n elements. So you take your training data and you sample with replacement a collection of examples, a collection of m prime examples. Sample with replacement means that the same example can show up multiple times. So you get a training set with m prime examples. You call your learning algorithm on that to get a classifier. And let's call that classifier CI. You do this n times, you get n classifiers. Think, for example, decision trees. And your final classifier is nothing but a voted version of these, a voted ensemble of all these individual ones. In other words, when a new example comes in, you ask all these n classifiers for what the label on this example would be. If the label plus is more frequent than the label minus, the final decision is a plus. The label minus is more frequent, the label is a minus. Doesn't necessarily have to apply to binary classification. Whatever label is most frequent in these among these n classifiers is the final answer. This is actually super easy to implement. The only thing you need is sampling with replacement, and that shouldn't really be a problem because NumPy and such libraries do that for free. They do it. It's one line of code. So here's another idea for your project. Use whatever learning algorithm you want, apply bagging on top. That gives you a new classifier. Yes.
Is there any guideline to how many samples you should drop on the training side?
Yeah, so one thing that I've seen is the number of samples that you can draw can be equal to the number of examples in the first place. Could be. But this is where it becomes a little bit of a heuristic. Um, if there are no, if you, for example, if each round you draw exactly one sample, that's not going to be great. If in each round you draw m samples, where m is the number of examples, then you might imagine your data set has 100 million examples. Then it becomes very slow. So the computational concerns also come in. Yes.
Or maybe I was a big example.
So sampling with replacement is, so imagine that you have a set, let's say, of 4 things, A, B, C, D. And let's say my goal is to construct a sample of three items. So maybe I pick C. And now if sampling without replacement means, because I have chosen C, so I'm going to construct a set of 3 things. Because if I'm sampling without replacement, that means if I've chosen C for the first position, C is out of the game, not allowed to pick C again. But if I'm sampling with replacement, for the next position, I can choose any of the 4 again. So maybe I choose an A here, and maybe I choose an A here. That's okay. But if I'm sampling without replacement, A and C cannot show up in the 3rd position because they are already picked. So in the worst case, if you sample with replacement, you might get a data set consisting of the same example repeated again and again. A very low probability event could happen. Yes. It does. It comes with statistical guarantees of robustness. It comes not learning theory guarantees, but more from the statistics side of things. So bagging is a general method. It applies for classification. It applies for regression. If you're doing regression, then your weak classifier produces a real number, right? How do you combine them? The final output is not a vote, but you just take the average. You have so each each CI produces a real number. You take the average of all those numbers, and that's the final output. If it's a classifier, then it produces a discrete label. You take the label that has the highest number of votes. The different versions of the data set that are constructed, they are called bootstrap replicates of the data. So that's a bootstrap replicate is just a fancy word for construct sample the data set with replacement. That's why it's called bootstrap aggregation. This part, in the name, this is really from here. And nobody says bootstrap aggregation. We just say bagging because it seems more catchy. So with regression and classification, bagging works, on many data sets, bagging works really well. It's a very useful tool to have in your toolkit. It's also a very, very simple thing to implement. Doesn't really matter what the underlying classifier is. Just add a layer on top, some code that wraps around it. That is, sample the data set with replacement, call your learner, do this many times, and you're done. It turns out that bagging leads to statistical improvements, especially in cases where mildly changing the data set can cause big changes in accuracy. Then bagging helps by kind of avoiding those drastic changes. It makes the models more robust to these sorts of changes. Here's an example of bagged decision trees. You create T bootstrap replicates of the data. You train your trees. You call your decision tree learner. It could be a tree. It could be a depth limited tree, whatever, to produce T trees. And the final prediction on out of bag samples is just another way of saying future example is the aggregated prediction across these three trees. In this picture here, you have each tree is a regression tree. It produces a real number, which means the leaf node is a real number. And if each of those produces some real number, you just average those outputs to get the final output. But then the cool thing about ensembles is, in addition to averaging these predictions, you can also measure things like, say, standard deviation, and you get more statistics about the quality of the prediction. Questions about bagging? Yes.
I have a more, I have a more general question on this. So, we've seen a decent amount like algorithms at this point. How do you usually decide the boundary for like in the given data set? What you can use it, you usually set like mathematic and that's
You want to know the answer that I like the most here? It is whatever algorithm I have efficient code for is the one that I'm going to use. That's, but then there are some guidelines here. Perceptron, and we're going to talk about support vector machines next, and then logistic regression. All of these are linear classifiers, and actually they tend to perform very, very similar. Average perceptron, especially. So among these three, my choice would be whatever works best. Or sorry, whatever is efficiently implemented. I really don't have a problem. If I know that the true concept, I don't know how, don't ask me how I know this, but if I know somehow, because I understand the domain, that the true concept is not linear, then I'll have to start thinking about introducing that non-linearity in interesting ways. I could do that by either applying some feature transformations, by blowing up the feature space, but then that increases the dimensionality, and that makes my learning, it could make my learning slower. Or I could use other ways of introducing non-linear models. In particular, these days, my preferred method would be using some sort of a neural network. Ensembling is always worth keeping in mind. In particular, if you're doing, any production code that needs to be robust, an ensemble is always a good idea. For instance, in particular, I think a version of boosting called gradient boosted decision trees, tends to be extremely widely used in certain industry applications where you don't really care about having the absolute state of the art with the largest neural networks, but you want something that's fast and most likely very good. So ensembling is always a good strategy. Even with neural networks, it turns out, I keep talking about neural networks because that tends to be the state of the art today. But even with that, it turns out that there are papers that show that, yeah, there's a neural network, but I ensembled multiple models and things got better. So these are just general guidelines. It's not about any one learning algorithm. I try to think about the problem, and also practical concerns come in. How much time do I have? How much compute do I have? So all of these things have to be factored in. There's a question on Zoom, and then I'll come to you. So there's an interesting question. The examples we've seen use consensus voting among models for final prediction. Instead, could you treat, I'm just paraphrasing here, could you treat each model as a feature and train a new model on top of these features? Would that improve accuracy? So the suggestion here is a new kind of an ensemble, where instead of voting, you have these T trees, all of them make a prediction, and then you get T predictions. Each one is a -1 or a 1, and you can train a binary classifier on top of that. Whatever binary classifier, you train your perceptron on top of that. That's a perfectly reasonable ensemble, and it actually works. It works pretty well, in fact. I'm yet to decide, but it's possible that maybe in homework 6, I might even make you implement that. Another question is, can you use an ensemble with different kinds of learners? Maybe half of them are decision trees and half of them are perceptron. Yes, you can. There's nothing here that says the ensemble has to be homogeneous. Yes. Bagging is an ensemble.
Okay. I guess so.
Yes. Well, a bagged decision tree is different from a bagged perceptron.
So,
Yes, you can. Yes, that's right. But let's not stop with this bagging. Let's consider another kind of an ensemble. This one's called random forest, and as the name suggests, it's about trees. Oh, there's a question? You could, yeah, you could, but just keep in mind that you're making your life complicated here, right? If you're going to do that, then you just it makes life with hyperparameter tuning, and it makes the computational expense pretty heavy. So that may not always be done. One of the things I did want to mention with bagging that's not true for Adabus is you can train the individual components in parallel. If you have 10 computers, you can train 10 different trees in parallel and then combine them later. Whereas you couldn't have done that with boosting because there's a sequential dependence. So let's talk about random forest. Random forest is basically bagging, but with, did you have a question? It's basically bagging, but with extra steps. So in bagging, you took bootstrap replicates of the data. You might take thousands of bootstrap replicates and just train decision trees if you're bagging trees on each of them. But in each case, all features are always available for each tree. In random forest, in addition to sampling the examples, you also subsample the features. Not all features are available. You subsample randomly a bunch of features for each round, and you ask the learner to use only these features to build a tree. You do that thousands of times, and then the rest of the story is the same. You aggregate them either by voting or by taking the average if it's a regression process. So it's just another sort of a complication, if you will, on top of bagging. Random forests are also very widely used. There are very robust implementations of random forests out there. Yes. Whatever is in the data set. I don't know why I put it there.
And you split, does that mean you split in the tree or for each new tree?
For each new tree, for each data split, yes. I recognize that the one line that is important for this slide has many problems. Other questions? We've covered 2 of the 8 words in that sentence. Okay, I'm going to wrap up this discussion on boosting and ensembles. We saw boosting, and the way I presented it was to present it as an answer to a theory that came out of a question that came out of computational learning theory, which is how boosting came about. Can we boost weak classifiers to get arbitrarily good? And the answer was a constructive proof, and by that I mean it was not just a proof, it was not just a statement that yes, we can do that, but it was constructive in the sense that it came with an algorithm. And that algorithm is add a boost. You should know what the intuition for add a boost is. You should be able to work it out on small examples. You should know the algorithm itself, and you should have a sense of why it works. The reason why add a boost might be working is because we are constructing a final hypothesis that is more complex than any of the weak classifiers can reach. And that final hypothesis, by the theorem says, can get arbitrarily close to 0 training error. And because we can apply pack bounds on top of that, we can also get close to 0. We can get low generalization error. But more generally, boosting is just an instance of the broader family of ensemble methods. Ensembling is always a useful thing to keep in mind anytime you're deploying machine learning, because I don't know why, it just tends to do better. Just like I think I mentioned with average perceptron, averaging always seems to do better than regular perceptron. Ensembling always tends to do better. The price you pay is computational, and it's also possibly overfitting, especially with add a boost. We looked at three kinds of ensembles: boosting, bagging, and random forest. Boosting, we looked at it in some detail. Bagging is so simple that you can just implement it. Hopefully, you can do it right after class if you want. Random forest specifically applies to trees, and it says basically bagging, but not all features are available for each element of the ensemble. Okay, I'll wrap up this lecture here. I was going to start support vector machines, but there are 4 minutes left, and I'll probably get to saying what a support vector machine is, and then I'll have to say that anyway on Tuesday. So maybe I'll pause for questions about ensembles or anything.
I would say that bagging
Does bagging maybe does not, because yeah, I would say it does not. You could, and that's related to the question about can we choose different hyperparameters for perceptron at each round for each element of the ensemble? You could, but then you have to come up with some policy for how that choice is made. And typically you don't go about that. Instead, what people do, and this is a very common way to ensemble trees, is just to decide upfront that the maximum depth of each element, each ensemble element is going to be 2, for example. And the thing that really changes is the data. And that way you get many, many decision rules of the same kind, of the same family. And that tends to be a more pragmatic way to go about it, because otherwise you need to come up with a reasonable approach for deciding all of those things, which could either involve thinking hard about the problem or spending some compute.
Then how it brings out the values, or for example, we are averaging them out.
Yes.
I just want to understand that how that's bringing up the value in giving that. I mean, is that bringing in the whole?
Oh, no, because what's happening is in each element of the ensemble is trained on possibly a different subset of the data. And because of that, any sort of noise that might be in some part, just by accident, kind of gets marginalized out. So you don't get a tree that overfits on any one kind of data or any one subset of data. So you get like multiple trees that are kind of that are robust in that sense. You're getting robustness, and that's why you're getting better accuracy. There was someone raised their hand, but then it disappeared. Okay. Okay, if there are no questions, let's wrap up today, and I'll see you on Tuesday.